Hello, everybody. And now we're doing section 2.3, the inverse of a matrix. The inverse of a matrix means, well, similar to what you would think, which is that if you have a matrix A, and the inverse would be another matrix B, such that if I multiply A times B, I get the identity matrix. Or if I multiply B times A, I get the identity matrix. Now, inverse matrices could only work if it's a square matrix. If it's not a square matrix, we don't talk about inverses. Now, let's move. A simple reason why it has to be square is because if it's not a square matrix, if I multiply AB, if A is an M by N matrix, Mike by November, so and I'm going to multiply it by B, well, B is going to be N November times something else. Let's say M, or A or whatever. So the point is that if I multiply AB and I multiply BA, I'm going to get two different size matrices and won't even, just nothing. There's nothing to talk about. So whenever we talk about inverse matrices, we'll always talk about square matrices. End of story. Now, if there is not every matrix has an inverse, but if there is an inverse, the inverse is unique. Unique means that there's one and only one inverse. And how do we see that? So if A is invertible, because if it's not invertible, there's nothing to talk about. We know that there's at least one inverse B. We want to show that B is the only inverse. So we know that AB equals I, which is also equal to BA. I'm looking at the very bottom of the page now. So let's assume, let's make a supposition. This is what they call proof by contradiction. Let's assume that A has another inverse, we'll call it C, and which means AC and CA also both equal the identity matrix, the N by N identity matrix. So we're going to show that B and C are equal to each other. And here's how we're going to do it. We're going to say that AB, we know that AB equals I, the identity. And I'm going to multiply both sides by C on the left side. So C times parentheses AB equals CI. But we know that matrix multiplication is associative, so I can write this CA parentheses times B equals C. But we also know that CA is equal to the identity, because that was our supposition, which means this is really equal to IB, and IB we know is just B, because that's what the identity matrix is. Well, look what I have here. B is equal to C. So we assume that B was one inverse. We were given that there was a one inverse, which we called B. We assumed that there was a second one called C, and we showed that B and C have to be equal. So therefore, a matrix is unique, and that's why I'm allowed to write A inverse. That's why I'm allowed to write A inverse, because if it wasn't unique, I couldn't write A inverse because it wouldn't be clear what I meant by A inverse. So A times A inverse is equal to A inverse times A, which is equal to the identity matrix. So now we want to do on this exercise, example 1, we just want to show that A and B are inverses of each other. And what we're going to do is we're going to multiply A times B, and then we're going to multiply B times A with matrix multiplication. I'd like you guys to do it now. Now, I'm not going to keep on saying this, but I always want you to pause the video and do it yourself. That being said, let's see what happens here. So AB, this is what you should have gotten for AB. And notice that when I multiply A times B, I wind up getting the identity. And when I multiply B times A, I also wind up getting the identity. And here's the steps. But now the question is, how would you find the inverse? See, here we just gave you two matrices. We told you that, how would you find an inverse of a matrix? Let's say I gave you like a matrix A, and I didn't tell you the inverse. Is there a way you could figure out the inverse by yourself? Without my, see here, I gave you both. I gave you the matrix, I gave you the inverse, but could you have done it yourself? So here we go. So here we're going to see how to do this. So now what does that mean? So the inverse has to be a matrix, x11, x12, x21, x22. These are the four, it's obviously it's going to be a 2x2 matrix. These are the different things. And I know that when I do the matrix multiplication, I'm going to get 1, 0, 0, 1. And that means, now when I do the matrix multiplication, I get x11 plus 4 x21, and over here, so this is all one. This here is just one entry. This thing here is just one entry in the matrix. There are 4 entries. It's a 2 by 2 matrix. There are 4 entries. This is the next entry. That's the bottom down there, and that's another entry right there. And I know that it has to equal the identity. That's what inverse means, which means that x11 plus 4 times x21 equals 1, and negative x11 times negative 3 x21 equals 0. So I could kind of like get out of this a system of equations, just like this, because I'm setting this equal to 1, that equals to 0. And similarly, I could do on the other flips, on the other 2 variables, I could go like this. Now I have 2 different sets of 2 equations with 2 variables, and you could solve this with matrices. You could solve this with systems of equations. Solve it any way you want. But when you solve it, you're going to get x11 is equal to negative 3, and x21 is going to equal 1. x12 is going to be negative 4, and x22 is equal to 1. And that you're going to get just by solving these 2 systems. But that means that the inverse matrix of A, so A, my original matrix was 1, 4, negative 1, negative 3. My inverse matrix is negative 3, negative 4, 1, and 1. And that is, and what I want you to do now is to use multiplication to multiply A times our supposed A inverse and see if you get the identity, and do it in both directions. Do A times A inverse and also do A inverse times A. Okay, now for us to move on, now I'm going to go through this. This is kind of a justification. Later, we're going to do a better proof of this. But for now, we're going to do a sort of a justification. When I did this, I had one system of equations, and I got 0, 1, which I could take this system here and write it as an augmented matrix. And I have a second system. I kind of had like 2 separate, I had a separate system over here on the right side. And I could also write that as an augmented matrix. Notice here's the coefficients and here's the constants. But the truth is, in order to notice that the coefficients are all the same. So in order to solve, we solve this by putting the coefficients into what do you call it, reduced row echelon form. So I may as well. So whatever I'm doing on this left matrix, I'm doing the same steps on the right matrix, because I have the same coefficients. So I may as well combine things to do it, save some time. So I'm going to join these matrices like this. So here's my matrix. Here's my original coefficient matrix. Here's the 1, 0 from here. And here's the 0, 1 from there. So now I'm going to do the same steps I would have done, my Gauss-Jordan elimination. And I finally get 1, 4, 0, 1, and I finally get over here. I finally get the identity matrix. Well, the negative 3, 1 winds up being the solution for this guy, and the negative 4, 1 winds up being the solution for that guy. Basically, what this means is that I now is that this negative 3, negative 4, 1, 1 basically winds up being the inverse matrix, because of the way I put it. This doubly augmented matrix, and that basically is the way we're going to find that. That is a way to find an inverse of a matrix. That's a good way to find an inverse of a matrix, meaning that you now this fancy thing here is going to make some more sense. What we're going to do, and we're always going to do, we're going to write our matrix A, and then we're going to write the identity matrix. We're going to join it to the identity. So A could be a 2 by 2, a 3 by 3, a 5 by 5, whatever A is. We pick the appropriate identity matrix. Then we go do all our steps to get A into reduced row echelon form. In other words, make A into the identity matrix. And whatever is going to be left on the other side is going to be A inverse. And you could always check and see that it's always going to work. In fact, it's always good to check to see that it works. And this is always going to work. Now, this is kind of, I wouldn't call this official or formal proof what I did, but it's a very good, it's pretty good. We're going to give like a little more of a formal proof of this process. But for now, I think this is awesome. So let's look at a problem. Yeah. By the way, I'll try not to use improper bad language, but there is a 4-letter word here. It's my least favorite word, work. Oh, I hate work. Anyway, let's, I thought I'm being hilarious. I guess I'm the only one. Let's move on. Let's find the inverse of this matrix A. So what you're going to do is you're basically taking this matrix, and you're writing it down here, and you're putting the identity matrix over here, the way, just for all the reasons we said, above. And we're going to use matrix operations. And oops, what just happened here? And we're going to use matrix operations to get this guy here to look like that guy down there. And these are all the matrix steps that we did. And what we're saying now is that the matrix on the there you go, this matrix here, -2, -3, -1, -3, -3, -1, -2, -4, -1. That 3x3 matrix is the inverse of our original matrix. And again, you could multiply it out just to verify it. Alrighty, or confirm it, whatever you want to say. Now, if we have a situation where there's no inverse, sometimes, like I say, not every matrix has an inverse, but this process will actually kind of bear that out. It'll kind of show that. So here's a matrix here. This matrix, I'm spoiler alert, this matrix does not have an inverse, but let's see what happens. When we start doing this process, we start adding the rows and adding the things and blah, blah, blah. And we're trying to put the left side of it into reduced row echelon form. But when I do that, notice that in the process, I wound up getting a row of zeros on the bottom. And I got numbers over here. But what does that mean? That would mean if I have a row of zeros, it's not possible to get this left side into identity matrix form. I can never. There's no way I'm going to be able to get a 0. I'm sorry. There's no way I'm going to be able to get a 1 over here and maintain the zeros. Like, for example, I could take half of row 2 and add it onto row 3, and now I have a 1 down here, but I also have a -3 halves. And if I want to try to, whatever I'm going to do to get rid of that -3 halves, that's how I use the 2 to get rid of it. In other words, I'll just keep on creating a bigger and bigger mess, and I'll never get a 0, 0, 1 here. So sometimes when an entire row, so you see when an entire row zeroes out, for example, that shows you that it's impossible for the matrix to have an inverse. Now, when we here this is a formula which we're just kind of giving you here. If A is a 2x2 matrix, now what I'm showing you now, it works for 2x2 matrices. It doesn't work for other matrices, but it's a very simple formula for a 2x2 matrix. If I have an A, B, C, D, those are the 4 elements in the matrix. Those are 4 entries, I should say, in the matrix. And if this is the original matrix A inverse is going to be 1 over AD minus BC times the D, -B, -C, A. And if you want to prove this, it's really very easy to prove. If I would take matrix A and join the identity matrix onto it and do the whole process that we did before, I would get, this is what I would get this for my, I would get this for my inverse. And it's not that hard. It's not that hard to do that. Or if I would do it the original way, I did it 2x2. Maybe remember up above here, before we did the fancy adjoining matrixing, we just we did it. We went like this. We put our 4 variables here, and then we solved all the equations and blah blah blah. So if I would do that, I would get that. I would derive that formula. So this formula is actually quite easy to derive, and this is a nice thing to know. So let's look at the inverse of matrix A and the inverse of matrix B. And now what's going to happen is that for matrix A, when I do AD minus BC, I'm going to get 4. and which means I'm going to basically, if you notice, I have to switch the A and the D, so the 2 and the 3 get switched. So then I have 2 and 3 here, and I have to just change the sign. In other words, original was A, B, C, D. So the A and the D keep their sign, but they get switched. The B and the C keep their position, but they change their sign. And so this is what happens after I do all that, but I have to multiply by 1/4, and this is A inverse. Now for matrix B, for example, B over here, when I do AD minus BC, I get 0. And that means you can't find an inverse because the inverse is 1/0. 1/0 is undefined. So POW, we know that this does not have an inverse. Now, whenever AD minus BC equals 0, let's go back up here. Whenever AD minus BC equals 0, that means that AD equals BC, which means that these guys are in proportion to each other. Which means if these represent coefficients of a line, then they would either be parallel or they would be on top of each other. Either way, there's no inverse. Parallel lines which never meet, and so forth. Okay, we got that. So now we're gonna look at some properties of inverse matrices, and here we are right now. Properties of inverse matrices. So if A is, well, this is obvious. This is pretty much by definition. Number one is that the inverse of the inverse is the original matrix, like duh. This says that if I have CA and I invert it, it's the same thing as saying 1/C times A inverse. This is not hard. This is not that bad. The inverse of the transpose is equal to the transpose of the inverse. And this says that the inverse of A to the K power is A inverse to the K power. So let's see if we can prove some of these. So for 1, 3, and 4, the key is the fact that the inverse of a matrix is unique. In other words, BC equals CB equals I, then C is the inverse of B. So property 1 says that the inverse of A inverse is A itself. And to prove this, let's take A inverse times A, which is A times A inverse, which is I. That means that I don't even know how to say this. It's pretty, how do I even say this? That means that if I would multiply, I'm not even sure how to, which means that A is the inverse of A inverse. All right, one is pretty, I think one is pretty, just the more you start explaining it, to never mind. Anyway, let's go on to the next one. Property 3, this guy over here. So let's prove this. Let's take CA. Let's prove it by just trying it. If it's an inverse, that means if I have 1/CA inverse and I multiply by CA, that means that CA is the inverse. CA inverse is this. That's So now if I do this, we showed that one of our theorems was that you could take the constant out of the multiplication. So I get C times 1/C times A times A inverse. But C times 1/C is 1, A times A inverse is I, and POW, we just have I. And if I do it the other side, if I do it the other direction, get the same result. And so there you go. So and property 2 and 4, that's left as exercises. For a non-singular matrix, the exponential notation can be extended. Well, what does non-singular means? Non-singular means invertible. So I can extend this, that A to the negative K is equal to A inverse to the K. And now I could show that A to the J times A to the K is equal to A to the J plus K. And A to the J to the K, like the power of a power, is A to the JK. And that's true for any integers JK. And by integers, I mean positive or negative, which is kind of awesome that these are famous laws of exponents. These are famous rules of exponents with plain numbers, but these same exponent rules also work with matrices, which is kind of cool and kind of awesome. Okay, so let's find the inverse of the square of a matrix. Well, we just learned that there's two ways we could do that. We could square the matrix and then find the inverse, or we could find the inverse and then square it. Either way, this is what you should get. This is what you should get, and but I like you to not close your eyes. Just look at the original matrix, work it out, and then see if your answer matches what we have right down here. But this is the answer right here. Okay, let's move on. Now we have the inverse of a product. And this is, again, pretty straightforward to prove. The inverse of a product is equal to the product of the inverses, but in reverse order. And the way to show it is to just multiply the product times the reverse order inverses. And when I do that, I get the B times B inverse cancels out. And then I just get the A times A inverse, which cancels out. And I have the identity. So this is a very, very, very straightforward thing to prove. And this could, we just showed it for just A, B. But even if it's like, A, B, C, even if it's like a whole slew of matrices, the inverse of this whole giant product is the product of all these inverses, but again, in reverse order. So that works out great. Now we want to find the inverse of the product. Here's an exercise. I want you to find the inverse of the product, but we're going to make your life a little bit easier. We're going to tell you the individual inverses, that A inverse is this and B inverse is that. Now you could have found A inverse by yourself, and you could have found B inverse by yourself by doing that whole, joining it to the identity matrix. But we're right now, we're saving you a little sweat, and we're giving that. So how do you find the inverse of the product AB? Very simple. I just take B inverse and A inverse. I multiply them, but in reverse order. I put the B first, B inverse first, and then the A inverse first. And this is the final answer that you all should have gotten. Okay, let's cancellation. Now, we had said that cancellation does not always work, but sometimes it does work. If C is an invertible matrix, then cancellation does work. Meaning if AC equals BC, then A equals B. Even though I made a big deal in the last section to give you an example where cancellation does not work, because it does not always work, but it will always work if C is invertible. And it's very simple to show. If AC equals BC, multiply both sides by C inverse on the right side, and then the C and the C inverse, and then do the associative property. The C and the C inverse cancel, and I wind up getting A equals B. Hence, that's it, cancellation. And for the second part, the proof is the same thing. I just multiplied by C inverse on the left side. So cancellation works if the matrix is if the common matrix is invertible, and that is awesome. Now, here's something which we can now prove easily, which is something we're kind of taking on faith before this. We could show that if A, which in this case is the coefficient matrix, A is the coefficient matrix here. If A is invertible, then AX equals B, which is again is a system of equations, has a unique solution. Means just one solution. Remember I said there's either 0, 1, or infinite. There's going to be one and exactly one solution. And to get that one solution, it's just going to be A inverse times the constant matrix B. And it's very simple to show, because if AX equals B, multiply both sides by A inverse, and that cancels, and I get X is equal to A inverse B. And I know it's unique because if it wasn't, if I would have an X, if I would had an X1 solution and an X2 solution, means I'm setting them equal to each other, but I could cancel the A's because we said A was invertible, and I get X1 equals X2. So any other solution has to be equal to the first solution. Now this is enormously powerful because it gives us a new way to solve linear systems of linear equations, which is awesome. So we want to find. We're going to use this new knowledge to solve a system of linear equations, a whole new way. What we're going to do is that we have three, now they're giving us three systems of equations, but if you look carefully, you'll notice that these three systems of equations have the exact same coefficients for X, Y, Z. The only thing that differs is the constants on the right side of the equal sign. So the coefficient matrix is 2, 1, 2, 3, 1, 3, 3, 1, 2, 4, 1. Now, normally I would torture you and let you have you go through the whole process of putting this into row echelon form, blah, blah, blah. But for now, we're just going to tell you that we did that work already, and this is the A inverse. Now, to get the solution set to solve these three equations, I just have to take my inverse matrix, multiply it by the constants, and pound. That's going to be my answer. So for the first problem, let me just show you here. The first problem where the constants were -1, 1, -2, I just take this A inverse matrix, multiply it here, and I get these numbers right there, pow. And it's super simple, amazing. It's amazingly simple. And here, I take the constants 485, multiply that by the inverse matrix that we had, and I get those answers. And it's a very, very straightforward, simple process of solving systems of linear equations that is multiplying by the inverse matrix. And that is awesome. Well, that concludes 2.3, and we will see you again next time. Bye.